This is College Mathematics first semester TDC Guwahati University. I am going to do sequence and series. Sequence and series. Supplementary problem set 2A. So here I am going to start from question number 3. This is 2A. I am going to start from question number 3. That is so that the following sequences are monotonically increasing and bounded. Where un any term, that's n by n plus 1. So to solve this, you have to do nothing, only you do un plus 1 minus un. So if it is greater than 0, then monotonically increasing. If it is less than 0, then it is monotonically decreasing. This is all you have to do. It is not so tough. So this will be equal to n plus 1 by n plus 2 minus n by n plus 1. So here your LCM is n plus 2, n plus 1, n plus 1 the whole square minus n into n plus 2. So this will be n square plus 2n plus 1 minus n square minus 2n and n plus 2 n plus 1. So here this cancels out. This is 1 by n plus 2 n plus 1, and this is greater than 0. So it is monotonically increasing, and un you can write it like this, n by n plus 1, that is equal to 1 minus 1 by n plus 1. So here you see that for n is equal to 1, un is equal to half, and it is less than 1 always. So your un is greater than half and less than equal to 1. So this is bounded. Now question number 4, that is question number 4. Here question is so that the sequence un where un is equal to 1 by n square is monotonic, decreasing and bounded. So here your solution. So here your un is 1 by n square. Again the same procedure. You do this is, if you do un minus un plus 1, that is 1 by n square minus 1 by n plus 1 the whole square. So this will be equal to your LCM will be n square, n plus 1 the whole square. So this is n plus 1 the whole square minus n square. So this is equal to n square plus 2n plus 1 minus n square by n square n plus 1 the whole square. So this is 2n plus 1 by n square n plus 1 the whole square, and this is greater than 0. So it is monotonically decreasing, it is monotonically decreasing, and your un it is greater than 0, it is greater than 0, but it is greater than 0, but it is less than equal to 1, because n is equal to 1, it is 1, and rest will be it is less than 1, less than 1, and all the values will be greater than 0, though this is bounded. All the values will be greater than 0, so this is bounded. Now question number 5, we have to establish. Question number 5, establish from definition that un is Cauchy sequence. Establish from definition that un is a Cauchy sequence, So now for this you have to take the help of Cauchy sequence, that is here your solution, here un is equal to 1 minus 1 by n plus 1, and um is equal to 1 minus 1 by m plus 1. So here, as per your theory, that is now what I am going to take, this is modulus um minus un, modulus. So this is um minus un, that is modulus 1 minus 1 by m plus 1 minus 1 plus 1 by n plus 1. So this will be 1 by n plus 1 minus 1 by m plus 1, and this is less than equal to 1 by n plus 1 plus 1 by m plus 1. So again this is less than 1 by n plus 1 plus 1 by n plus 1. So we can say that this is less than 1 by k plus 1 plus 1 by k plus 1. So this is equal to 2 by k plus 1. Here see, as per theory as per theory this is less than epsilon, because less than epsilon, since for epsilon greater than 0 and k belongs to n, 2 by k plus 1 is less than epsilon. So epsilon, so it is a, so this is a, we can say that here this proves that this proves that un is equal to 1, un is equal to n by n plus 1 is a Cauchy sequence, Now rest this you can do it yourself. Now question number 6, prove that the sequence un where un is equal to 3n plus 1 by n plus 2 is monotonic increasing and bounded, find its limits. So here what you have to do, that is bounded, it is bounded and so here to prove that it is monotonic increasing, you have to take un plus 1 minus un, so this will be 3 n plus 1 by n plus 1 plus 2 minus 3n plus 1 by n plus 2, so this will be 3n plus 4 by n plus 3 minus 3n plus 1 by n plus 2, so this will be your n plus 3, n plus 2, 3n plus 4, n plus 2 minus 3n plus 1, n plus 3. So when you solve this, it will be your 3n square plus 6n plus 4n plus 8 minus this will be 3n square plus 9n plus n plus 3, and this will be n plus 3 n plus 2. So if you solve this, it comes out to be 5 by 3 and 10 cancels out, 10 cancels, 8 minus 3 5, n plus 3 n plus 2, and this is greater than 0, so it is monotonic increasing. So this is monotonic increasing. And for bounded you have to do something. For bounded, that is for bounded, your un is 3n plus 1 by n plus 2, so 2. Now from here let us take mm, u uh, un minus 1, because I have done this as it is done in your example here. It is done in your example. uh, hmm. It is done in your example, that is un minus 1. So um, here this will be 3n plus 1 by n plus 2 minus 1. So this will be equal to n plus 2, 3n plus 1 minus n minus 2. So this will be 2n minus 1 by n plus 2, and this is greater than 0 because your n belongs to natural number, because your n belongs to sequence here n, because your domain is natural number, because your domain is natural number in the sequence. It is the theory which is given to you that the domain f, your f, see your f whose domain is natural number. So because n belongs to natural number, so this is greater than 0. This is greater than 0, that means your un is greater than 1. So your un is greater than 1 here. In your in the example given here, it was see, in the example given here, un is less than 1, so it was bounded above for every n belongs to natural number. So here your un is bounded below. This will be bounded below. This will be bounded below. Mm. So this will be bounded below. Means it is an idea. From this idea you can see that from this, since n belongs to natural number, so here since the n belongs to natural, from here you can make this idea that this is numerator, your numerator is greater than denominator. You can see that the numerator is greater than denominator, or you can prove it. You can see that 3n plus 1 minus n minus 2. So this comes out to be 2n minus 2. So here you see that this is value is greater than equal to 0, since for every n belongs to natural number. So from here we get a conclusion that 3n plus 1 is greater than n plus 2. So from this we can conclude that your this minimum value is 1. So if you take n is equal to 1, this will be 4 and 4 divided by 3. So your value will be greater than 1. So your minimum is bounded, so it will be bounded below. So this is the idea I have taken. Now we have to find the limit, and third you have to find out the limit. So to find the limit, that is limit n tends to infinity, your 3n plus 1 by n plus 2. Here again limit n tends to infinity, n common, 3 plus 1 by n common, 1 plus 2 by n. So n cancels out, so this will be equal to 3. So this is your answer. Now question number 7. here you see examine for convergence of the following following sequences whose nth terms are, this is a, n plus 1 by n plus 2. We take the limit n tends to infinity, so here n common, 1 by n, and here this is n common, 1 plus 2 by n, so this cancels out and this becomes 1. So we get a limit, since we get a limit, so here you see this is here, since it is mentioned here that this is the limit here, this is the 1 is the limit. So if you for convergence, it is shown that it is in the example, it is also shown here that when we take the limit, see, in see here a finite number, when limit n tends to, you get a finite number, so hence it is given same type of questions. It is given that here you can see when you get a finite number, so un is convergent. So here since we get a finite number, so therefore hence this un is convergent. Now your next question is b, that is we are again going to take the limit n tends to infinity, n square by n plus 1, this will be limit n tends to infinity, n square, here n common, 1 plus 1 by n, so this cancels out, so this becomes infinity. So here un is divergent, so this is divergent. Now again your third C, if you take limit n tends to infinity, 2 plus minus 1 to the power of n, so such type of question is, it is solved here, you can see a type of this question is solved here. This will be equal to 2 this will be 2 plus minus 1, that is it is equal to 3 if n is even, and it is equal to 1 if n is odd. So therefore your limit n tends to infinity, un is not unique, so un is not convergent, so this is not convergent, so now your next question, this is just every convergence sequence is bounded, this is all given in your book, and prove the sequence, this is also solved in your book, you can see this is also solved, question number 9, this is solved in your book, this is the question. same question, it is solved in your book. X modulus x less than equal to 1. This is solved here in your book, it is solved here, so you can do it from here itself. And now your question number 11, question number 11 question number 11 you can see your question number 11 is question number 11, that is, let your un be a sequence such that your u1 is equal to root 2 and un plus 1 is equal to root 2 un for every n greater than equal to 1. Prove that un converges to 2. So how to solve this? So here u1 it is given root 2, so u2 this will be 2 u1, so this will be 2 2. Now if you do you see from here, you can see that means your u n plus 1 the whole square minus u n the whole square, this will be root 2 un the whole square minus root 2 un minus 1 the whole square. So this comes out to be 2 un minus 2 un minus 1, so this will be 2 common, so un minus 1, and from here this side you will find that un plus 1 minus un into un plus 1 plus un. So here again this is un plus 1 minus un plus 1 plus un. Here you see that this will be this is this must be converges to, that means so one thing that is we have to do is that here you see, since this is greater than 0, so to be this greater than 0, your un plus 1 minus un should be greater than 0. So here un plus 1 is greater than un, so so it is therefore this un is monotonically increasing. This is increasing, monotonic increasing, and now we have to prove that it converges to 2. So to prove that it converges to 2, to prove that this it converges to 2, we have to do one thing, converges to 2, that is let your limit n tends to infinity, un is equal to L, and L, then limit n tends to infinity, un plus 1 is equal to L. So here your un plus 1 is equal to root 2 un. So un plus 1 the whole square is equal to root 2 un the whole square. Now if we take limit n tends to infinity, here limit n tends to infinity, this will be L square, and this will be this will 1 minute, squaring both sides, so this will be let me do one thing here. That is, you take now un plus 1 the whole square, n plus 1 the whole square will be equal to root 2 un the whole square. So this will be un plus 1 the whole square is equal to 2 un. So now if we take limit n tends to infinity, un plus 1 the whole square is equal to 2 limit n tends to infinity un. So this will be L square is equal to 2L. So L square minus 2L will be equal to 0. So L minus 2 equal to 0. So here your L can never be equal to 0. So therefore L is equal to 2. So the sequence 2. So the sequence converges to 2. So the sequence converges to 2. This is your answer. So now question number 12. Here you can see question number 12. Let un be a sequence where your un is equal to 1 by n sine n pi by 2. Prove that the sequence is convergent. So here you see, if I take limit n tends to infinity 1 by n sine n pi by 2, again limit n tends to infinity 1 by n, and we know that the value of sine, it lies between -1, that is sine value of sine x, it is greater than equal to -1 and less than equal to 1. So n tends to infinity, so this will be equal to 0. Therefore it is convergent. Now question number 13. Prove that the sequence that is un is convergent where un is equal to 1 by n square 1 plus 2 plus ... plus n. Now limit your n tends to infinity 1 by n square 1 plus 2 plus dot 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 plus n. This is n. So this will be limit n tends to infinity 1 by n square, and the sum of this formula is n plus 1 by 2. So here limit n tends to infinity 1 by n square, n again n common, 1 plus 1 by n by 2. This cancels out, so this will be limit n tends to infinity, then 1 plus 1 by n by 2. So this is 0, 1 by 2, a finite value. So this is convergent. Now question number 14, you can do it yourself. So I'm going to question number 15. This is question number 15. Determine 14, you can do it yourself. This is given in your example. Proof is given in your example, so you can do it from there. Determine the limit of the sequence un, where un is equal to 2n plus 1 by n plus 5. So I am going to take the limit n tends to infinity, n common, 2 plus 1 by n, and here n common, 1 plus 5 by n. So cancels out, this is 0, this is equal to 2n. Now question number 16. Question number 16. Question number 16. Find limit n tends to infinity root n plus 1 minus root n. You just rationalize it. That is root n plus 1 plus root n and root n plus 1 minus root n plus root n. So here this will be limit n tends to infinity. This will be n plus 1 minus n by root n plus 1 root n. So this will be limit n tends to infinity 1 by root n plus 1 plus root n. So n tends to infinity, this will be 0. Now question number 17. Question number 17. Prove that the sequence un is convergent and find its limits. Find its limit if un is equal to 1 by n cube 1 square plus 2 square plus n square. So here limit n tends to infinity 1 by n cube, and this sum of this formula is n plus 1, 2n plus 1 by 6. So limit n tends to infinity 1 by n cube n into n 1 by n by 6. This cancels out, so this is 0, this is 0. This will be 1 into 2 by 6, that is equal to 1 by 3. This is your answer. Now question number 18. Question number 18. Apply Cauchy's general principle of convergence to show that first un is divergent if un is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by n. So to prove this, let us do something, that is you have to prove it like this. To prove this, your un plus p, this will be 1 plus 1 by 2 plus 1 by 3 plus 1 by n plus 1 by n plus 1 1 by n plus 2 plus 1 by n plus p. This will be, so here un plus p minus un, this comes out to be 1 by n plus 1 plus 1 by n plus 2 plus dot 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 plus 1 by n plus p. So here we can say that this is less than 1 by n plus 1 1 by n plus 1 plus dot 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 plus 1 by n plus 1. So now again what we get is 1 by n plus 1 1 by n plus 2 plus dot 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 plus 1 by n plus p is less than p, because here there are p terms, because we have taken n plus p, no, so up to there, since there are here there are p terms, so p by n plus 1, because from up to this n and rest this is p, so this is p terms, and this is not less than 1 by n plus 1, so this is not less than 1 by n plus 1. So here we get that, therefore un plus p minus un is not less than epsilon, so it is divergent. So it is divergent, because for convergence the case is it must be less than epsilon. So vice versa, if it is not less than epsilon, then it is what we can say, then it is divergent. That's all. And now I am going to question number 19. Question number 19, examine the convergence. So here you see this series, see question number 19, here it has given an hint, that is un and nth term, that is n by n plus 1, and in the second case also it is given that your nth term is n by n plus 1. But if you see here, your second series, your nth term is not n by n plus, because see your denominator is so your numerator is greater than the denominator. Your numerator is greater than the denominator, and here your nth and un is, it is given that n by n plus 1, un is given n by n plus 1. So if you take 1, then 1 plus 1 2, 1 by 2. If you take 2, then 2 plus 1 3. There is no 2 by 3 in this sequence. So this from my point of view, this does not satisfy this. And second, for un, this here you can see clearly your numerator is greater than the denominator. So this question, there is some controversy, so I am not going to solve this question. I am not going to solve this question. This is all about sequence and series.